Hello guys, in this video I'm going to talk about the maximum likelihood method ML method but for multivariate Gaussian distribution. So in the last lecture we saw the univariate Gaussian density. Now we are going to take the likelihood as a multivariate Gaussian distribution. So we saw that we could have different feature vectors. So we used to denote there are these different feature vectors x. So now you can always have multiple feature vectors. So one feature corresponding to the size and other feature say corresponding to the luminance. So we are going to see multiple feature vectors, that is a multivariate Gaussian distribution, and how can we apply the ML method on this. So the notations are quite similar. So here also I am so these were the notations of univariate Gaussian density. So di is equal to x1i xi2 up to xin. So let me just quickly recap you what is this. So di is nothing but a set. So di is the set of one class, so say a set of sunflower. So it will contain all the images of sunflower. D2 set of rows contain all the images of rows. xi1 is basically the first image. So what are the feature vectors for this first image? So it may be say x1, the size is say some x1 is equal to 6, the size is 6, and the luminance say x2 is equal to some number say 15, some luminance, right? So that is this. So here please note that the xi1s will be a vector of d dimensions. So as in this case there is x1 which is size and x2 which is luminance. So this is this x1 which is size and x2 that is luminance. So in this way you can have d vectors, d features over here. So that will be d. Right, so what we have to estimate? We have to estimate the parameters, that is mu and sigma. That is what we have to estimate. Here also note that mu is also a vector now, because it will have the mean of all the sizes, the mean of all the luminances, etc. So the mean of all the sizes will be over here, mean of all the luminances will be here in the story. So mean is a vector. Similarly here sigma I is a matrix, covariance matrix. So what does that say? That says what is the variance of class 1 feature 1. So feature 1 variance, then the covariance of feature 1 and feature 2, the covariance of feature 1 and feature 3, and those all will come in the columns. Similarly the covariance of 2 with respect to 1, 2 with respect to 3, that is second row, like this. So you'll have a covariance matrix. So note that here you actually don't have to calculate two parameters, but you have to calculate d parameters for the mu. So that is the d mu's that you get, and d into d, that is d square parameters for the matrix. But if you closely see, this sigma I is always a symmetric matrix. So every element sigma ij of this element will be equal to sigma ji, because the variance of two with respect to 1 is equal to the covariance of 1 with respect to 2. So these two elements are similar. So because of this d square just uh, comes down to d into d minus 1 by 2. So these are the diagonal elements and say the upper diagonal elements that we will have to calculate. Right, so now we have the probability. So we are assuming that the likelihood, this is the likelihood of the parameters. So we are assuming that the likelihood is a Gaussian distribution. So this is a multivariate Gaussian distribution that you can see over here. Only note that now everything is going to be vectors and matrix. So this is a vector, hence I am denoting a bar. This is a vector, this is a matrix. Okay, I forgot to put the inverse over here. There is this inverse over here. This is a vector, this is a vector. So this was for xin. So we talked about this. in the last lecture. So what are we actually doing is we are changing the means and trying to fit the Gaussian on this data, and we are seeing the we are calculating the probability of every x with respect to the particular mean that we are taking. So please refer to my video of Bayesian parameter estimation if in case you have not seen this. So this is the same case, it is just that now these are 2Ds. Now there is a new dimension that is going to come, a new dimension which will tell you luminance. So that is the only thing that is added over here, nothing else. So this is for a particular sample. So here, because it is 1D, it will be say in on this line, the samples will be on the line, but when there will be 2D, so the samples will be on a plane, because there is this two-dimensional plane, one feature vector, other feature vector. So we are calculating the different probabilities xin given theta I bar like this, assuming that it is a multivariate Gaussian distribution. So next, the whole probability for this di, the whole set, will be nothing but multiplications of individual probabilities of every element, because we have taken an assumption that the samples are independent of each other, which means that if a sample is at 3, that will give no information about what the next sample will be. So that just says that if the size of this sunflower is 3, so this will give no information about the size of the next image. So that is an assumption that we are making, which holds good for most of the cases. So yeah, so this is multiplications of all the xi's. So this will become product n is equal to 1 to ni. Remember, there are ni images in one particular set, so it goes from 1 to ni. So now we had discussed about this also, that even if say one sample goes very out of the range, the Gaussian, the actual Gaussian will have some value with for this point as 0.0001, which will make the because we are taking a product of all the samples probability, so the this tends to 0 because of this thing. So hence what we do is we take a log. So we are taking a log of the likelihood over here, so that is just nothing but the log of this thing, so it will becomes, the product will become summation over here, right? So now we are just putting the whole equation, this beautiful equation, we are putting this in this this summation, so basically yeah, over here. So and taking a log out of it, so you can see that there is this determinant raised to half sitting over here, so that because it is in the denominator, it will become minus half log of the determinant minus, there is this d by 2, so that will come up, so minus d by 2 log of 2 pi minus half, so log e becomes 1, so minus half e x I n bar minus mu I bar, the whole transpose, this things comes. So the next step that we did was basically to maximize. So we have got a plot like this. So this was for a single dimensional case. For a two dimensional case, this will be a 3D plot, right? So we have to maximize this plot, we have to find this value where the theta is maximum, right? Sorry, the p of di given, the likelihood is maximum, and we have to find the value of theta for which this is maximum. So what we do is we calculate the derivative, we calculate the first derivative and then equate it to 0. So here, because we have so many parameters, we have d means and we have d into d minus 1 by 2 covariances. So what we'll have to do is we have a mean vector. So we have seen that there is a mean vector, so we are actually differentiating this whole term by a vector, that is d mu I. So this is going to be equal to a 0 vector, because you have to equate every mu I differentiation with every mu I to 0. So this is now going to be a vector, So we are going to differentiate this with this, then this, then this, and then equate everything to 0. So this is going to be a vector. Similarly, differentiating with covariance matrix is going to turn into a 0 matrix. So because we have so many terms, so we'll have to differentiate this function with respect to this, and that will come over here. We'll have to differentiate with respect to this, that will come over here. So we'll have like this D cross D matrix. So this should be equated to a 0 matrix. So that is what we are going to do in a few minutes from now. So because there is this whole sort of vector differentiation and matrix differentiation, so we'll need some relations. So I'll keep this relations handy. We'll see where we'll need these relations. Let's see. Okay, so we have this expression over here, this beautiful expression over here, and we are going to differentiate this expression first by the mu I vector. So we are going to differentiate this with respect to mu I and equate it to 0. So if you see carefully, there is this sigma I term sitting over here, which will become 0 because differentiation of sigma I with respect to mu I, it is constant as we are taking partial differentiation. So this is 0. This is actually a constant, so this also becomes 0. Now this is the part that we are going to have to differentiate. So I have written this part over here. We will first simplify this part, and then we are going to do our further calculations. So for simplification, let us just take an example so things would be clear to you. So here the first thing that we have is xin bar minus mu I bar the whole transpose into x summation I this is sigma I inverse xin bar minus mu I transpose. So let us take an example. Xin is half, mu I is 2, not half. This is a vector 1 2, this is a column vector. So remember when I told about notations, so these people write in column vector notation. So xin is this, mu in is this, and let sigma be this. So now when I say xin minus mu in transpose, so this can be written as xin transpose minus mu I transpose. So there is no n over here. So how can I do this? Because xin minus mu in is nothing but 1 minus 2, that is minus 1, 2 minus 3, that is also minus 1. So this is xin minus mu in. Now if I take the transpose of this, this becomes like this. So this is equal to, when I take the transpose of xin, so it will become 1 2 and 2 3, and you take the minus. So 1 minus 2 is minus 1, 2 minus 3 is minus 1. So hence this thing can be written as individual transpose. So that is the first thing that I have done. Xin transpose minus mu I, and the whole transpose is written as like this. You can take individual transposes. Next, what you have to do is you have to multiply this thing with sigma I inverse. So if you take this as an exercise, when you multiply, say, this whole minus 1 that is xin minus mu in transpose into this comes equal to multiplying first xin into this, then multiplying mu in into this and taking their minus. So this is what is essentially I am talking. So you can basically separate this out. That is what we call distributive property. So I am multiplying sigma inverse with this, so there will be a I over here, and multiplying sigma inverse with this. So this is what is happening. Next what I do is so here this term is as it is over here. Next what is basic multiplication that applies to matrix also. So this term will be multiplied to this term, so that gives you xin transpose sigma inverse, so there is a I over here, into xin, then this term into this term, which will give you this term, then this term into this term, which will give you this term, and this term into this term, which will give you this term. Now please work out this exercise. When you say multiply xin, so I am taking 1 2, so when you multiply 1 2 with say 1 2 2 3, so remember covariance matrices are symmetric, so their inverse will also be symmetric, please remember that. And then you have there is a transpose sitting over here, so this will be like this 1 2. So there is 1 2 transpose into this matrix, into you get mu, so that is 2 3. So please calculate this. When you calculate, you will get it 34. Also when you calculate this, so this is what, this is 2 3 1 2 2 3, that is so mu I transpose is 2 3, then 1 2 2 3, that is some this thing, and then I multiply 1 2, so that is this thing. So xin summation sigma and mu I. Similarly so here, so this also comes out to be 34. So we basically see that this thing is always equal to this thing, so that is proved mathematically. I just gave an intuition of how it is coming. So hence we can write this as 2 times xin transpose sigma I mu I. So you can write it write over here mu I transpose also. I just took this, that's it. So now we are sort of ready for differentiation. So we had this this equation, and here this was constant, this was constant. There is this summation that is lying outside, and there is this important term that we have converted to this term. Now let us see the relations. Right, so here if you see xin transpose sigma inverse xin, so this again does not have any part of mu I. So remember, we are differentiating it with mu I, so this part, right, so what we have to do is we have to just differentiate this, because everything else was a constant. So when I am differentiating this thing with respect to mu I get a 0, because there is no mu I term. Now when I differentiate this thing, so that is xin transpose sigma inverse mu I bar, so we have a relation that says if my z is x bar transpose my bar, where m is a square matrix, so differentiation of z with respect to x bar will just give you my bar. So this is what is happening over here. If you see here, there is minus 2 times xin transpose sigma inverse mu I bar. So here if I derivate it with mu I, so there is this mu I sitting over here, and there is this x over here, so which will make this as sigma inverse mu I. So this was this relation, I'm sorry. So here y, so here we are differentiating with respect to x, so therefore y is constant with respect to x. Similarly we are differentiating with respect to mu I, so x is constant with respect to mu I. So this is this relation that is following. So x is y over here, m is the square matrix, and here x is with which we are differentiating. So for this the result is simply m into y bar. So m, that is our sigma inverse, into y bar, so that is y is this, and 2 is a constant, so it will be as it is. Next what we have is mu I transpose sigma I mu I bar. So this relation is like over here relation 2, which says that if we are differentiating with respect to x, you have that x transpose over here, and x, and m is a square matrix. So if M is a square matrix, what result you get is 2m times x bar. So this is a sort of, this is square sort of thing, because there are two, so there are square, so that makes it 2 times mx bar. So here you can see I'm differentiating with mu I. So there is mu I transpose and there is mu I over here. There is a square matrix over here. So this will make it 2 times mx bar, 2 times m x bar, which is mu I over here. So this is what we have done. Next what we are doing is, we will take this, so this 2 will get cut, this 2, this 2 will get cut, the minus will become plus over here, and this minus will become, this plus will become minus over here, and we are equating this to 0. First derivative is equal to 0. So this is the equation that we are getting. Next what we do is we take this term over there. So I am taking this term over here, and we get this expression. Now since this is these are all matrices, so what I'll do is I'll pre-multiply by sigma I on both the sides. So I can pre-multiply by sigma I on both the sides. So I'll get this. This was only to basically cancel both of these. So sigma I into sigma I inverse will give you nothing but an identity matrix. So here you will get an identity matrix, and here you have a mu I bar, and here you have xin bar. Now remember, there is no n term over here, so this is just basically adding mu I ni times, so that is giving you ni into mu I bar is equal to, this is the summation. Now there is a I, so that into anything will just give you the same thing. So ni n is equal to 1 to ni xin. Take this ni down, so you get your mu I, which is 1 upon ni summation n is equal to 1 to ni xin bar. So you can see this is the same formula actually that we got, just the case over here is xin and mu I bar are vectors over here. So what essentially you have to do is, you have these different feature vectors. Mu I will be nothing but the addition of all the feature vectors, the first feature vector, the addition of all the feature vectors of the different images. So you have say xi1 for this image, then you have xi2 for this image, xi3 for this image. You add all the sizes and you take the mean, that is the mean size. You add all the luminances and take the mean, that is the mean luminance. So that is what ML method is telling you. If you have a Gaussian distribution, just if you and you want the mean parameter, just take the individual features and just take their average, a simple average, and that will give you your desired mean. So that was actually all for my this video. Now a small exercise, you can do this same derivation for the covariance matrix. So next thing that we had to do was differentiate this thing with respect to summation of sigma I and equate it to a zero matrix. So you will have to derivate with respect to this. So this, I guess I'll upload it in say some near future. I'll not upload it in now. So I recommend you to please solve this once. You will need these relations for that. So please take these relations in your mind and try to solve it on yourself. It is quite simple. So I'm going to upload a video, but not now. So that will be good for you. You will understand the concepts also. So that was all for this video. In the next video we'll start with maximum a posteriori parameter estimation method, MAP method. So thank you so much for watching. Thank you.